Okay, quiet down, please. I'm going to get started. So today what we're going to do is we're going to finish up the sort of chemistry of nitrogen, and then what we'll probably do is, if there's more time, we'll sort of do a little bit of a refresher on aromatic chemistry and amines, which are going to be the bulk of the quiz next week. So, so it's sort of I made the comment last week that much of the chemistry that you end up seeing in this specific chapter involves the conversion of this sort of R group to some other leaving group. And one of the things that we saw last week, discussed last week, for example, is that if you take a molecule of aniline, right? And if you take aniline and you go ahead and you treat it with basically NaNO2 and HCl, right? What you're going to get to is sort of nitrogen leaving group. In this case, it's probably going to exist as something like salt, like this. Then we saw that you can do lots of different functionalizations. So again, just so you can remember through the mechanism, we sort of pointed out how when these two react together, effectively what you're going to have is an activated form. There's a few different ways you could reasonably draw a mechanism for this process. Bless you. So again, one possibility would be to sort of draw it in this form, you know, have sort of group leave and have your electrophilic species be this molecule here. Alternatively, you could draw it with the nitrogen sort of getting at this sort of protonated state, right? And then you could add it in there. The sort of net result is effectively the same. You're just going to do a dehydration process. So either of these types of systems, if you were asked for a mechanism, would be fine. I think the book shows this one. You know, I think they're basically both saying the same thing. We'll get back to some things further on down the road, but the sort of general idea is that once you have these types of species, right, you're going to get to a compound, right, where at a certain extent you're going to have to eliminate water, right, and that's going to lead to your sort of diammonium salt, okay? So from this intermediate, we discussed a few different transformations. In fact, the book has a sort of a nice little table that sort of succinctly points them all out. That would be, what section is this? It's 23, I'll write it down in a second. 23.8e. Again, it has a table that discusses a lot of the different transformations that you can do from here. And we went over a lot of these last week, right? So it turns out if you take this compound and you treat it with water, then you're going to effectively do nucleophilic substitution on there, and you can get compounds like phenols. It showed a series of halogenation reactions that you can do. One that we really didn't discuss was with a sort of tetrafluoroborate compound. In this case, you end up getting fluoride. So it effectively goes right down the sort of row of these. If you take this molecule and you treat it with HX, so different halogens, so hydrochloride, hydrobromide, HI, HCl, HBr, and sort of the copper version of that, what you'll end up getting to is various halogens. Okay, this is their Sandmeyer reaction. So copper is sort of needed through this process. The mechanism probably involves coordination and helping assist in the leaving of that nitrogen compound. And then the one other that's probably worth remembering is H3PO2, which we'll just get rid of that altogether. And as we'll see, in particular case, the sort of halogen functionalization, especially in the Sandmeyer case, we'll learn a little bit about cross-coupling chemistry next week. And in particular, the entry into these halo aromatic systems is really going to open up your ability to make substitutions around the aromatic, because there's a lot of ways in which we can make these transformations. Felix, last week, Felix brought up the question of regiochemistry for this, in terms of halogenation would end up on a different carbon. The book doesn't discuss any of that, and in fact shows examples where it goes to the same position. So it's probably best to sort of think about this chemistry. I double-checked because I could see where your thought process was. But I double-checked, and it's perhaps best to think about much of this chemistry going through sort of a cationic aromatic system. So just the nitrogen, you can just think about the nitrogen leaving, generating this carbocation species. So you're not going to necessarily scramble any position on there. It's just going to end up back where it would be. But certainly I can imagine situations where that may end up being the case. But I think for this sake, we should just stay in this form. In the case of H3PO2, this is the one that I actually have a question on the worksheet where I basically say, show the product and propose a mechanism. And the mechanism of this actually isn't really known. Certainly not in your book. And I looked it up and I tried to see if I could find something that was reasonable. But I think the mechanism of this process isn't fully understood. So you're not going to be responsible for it. One way that you could at least think about it, if you want to sort of rationalize it, is that this could be a sort of a source of hydride. So HP sort of two forms of this that you can imagine. So either in this form here, or in sort of this form here. And again, something that, again, I really don't know how the mechanism behaves, but my guess is that it would probably behave via this intermediate here, which is the high reactive intermediate, sort of helping decompose the nitrogen. So again, if you're kind of curious, we can try to flush out a mechanism upstairs in my office hours. So you're not responsible for this mechanism, but if you sort of want to rationalize it, you might be able to think about this sort of being like a source of hydride, even though I don't think that's what it is at all, but at least in terms of trying to think of what's happening, you could sort of think about it that way. But you're not responsible for the mechanism of this reaction. In these cases, I would just think about the sort of copper coordinating the nitrogen, assisting in generating this group, and then at that point you have the chloride, which would attack in. Okay? And then the same thing with like water, right? Nitrogen's going to leave, and you're just sort of getting that there. So you can simply think of it as SN1 like chemistry. You're going to generate that carbocation species, and then nucleophile will attack. Okay? So this is sort of diazonium species within aromatic chemistry, so from aniline derivatives. Again, where you can find it, we'll perhaps do some synthesis problems on aromatic chemistry at the end of the class today, just sort of getting us thinking about all the reactions that we've learned. We know how to, for example, nitrate aromatic groups. We know how to reduce them, and so you can imagine generating anilines through that sort of approach and perhaps getting into these other avenues. The one other example along the lines of nitrogen leaving groups that I wanted to bring up is a reaction that's very analogous to sort of pinnacle rearrangements. So if you remember in a pinnacle rearrangement, we just refresh on the pinnacle rearrangement. right? What's going to happen in a pinnacle rearrangement is if you take this molecule and this molecule, in fact called pinnacle, you're going to protonate. You treat this with acid. You're going to protonate this compound, and what you're going to get to is a species where after you lose water, you have a sort of a cation. Right? And one of the things that's special about the pinnacle rearrangement is that, again, we've seen last semester alkyl 1,2 alkyl shifts where you get sort of an alkyl migration moving from one area to the other. And the pinnacle rearrangement can actually take place fairly quickly. So this is a migration, again, of that sort of methyl group over the adjacent carbocations. Again, you can sort of think about this as an extension of hyperconjugation. The bond with those two electrons in it are being pulled towards the cation. Then the entire bond is moving over. It's a little bit counterintuitive based upon what we've seen in the past. What this is going to lead to, right, is then a new carbocation, which is very stable, right? And in fact, this is just going to very quickly polymerize down, and following deprotonation, you'll get to the ketone. Right? So this overall mechanism effectively involves generating a leaving group. Right? You're going to generate a leaving group. You're going to generate a cation, which is going to migrate fairly quickly and with a certain degree of predictability based upon the fact that you're generating a carbocation that is resonance stabilized. Right? And then simply looking at the resonance form, deprotonating, you can get to the ketone. So as you might imagine, in cases where you have sort of 1,3, sort of draw the analogy, in cases where you have a 1,3 diamine, if you were able to take that amine, right, and make it into a leaving group, you might imagine similar chemistry taking place, right? And so, as it turns out, similar types of transformations to the pinnacle rearrangement can take place. You take this compound, you treat it with HCl. And again, we can go through the mechanism of this process, but what's going to happen here is analogous to the pinnacle rearrangement. You're going to generate a nitrogen leaving group, right? So this is just analogous to pinnacle. You're going to get that leaving group to take place. And then you're just going to generate a cation. So it's the same exact reaction. There's really nothing new about this reaction than what we've seen in the past, right? It's virtually identical to the pinnacle rearrangement, with the only difference being that instead of a 1,2 diol, in this case you have an amino alcohol. And there's some advantages to this, right? In the case of a pinnacle rearrangement, if you were to take this molecule and you treat this with acid, if you have, say, different groups over here, right, it might be difficult to determine where you're going to protonate first, right? So, in fact, this proton source could have gone on this oxygen or it could have gone on this oxygen, right? And so in the case of this analogous transformation, what you have is a nitrogen and an oxygen. So you can actually, if you can get to that 1,2 diamine, or sorry, amino alcohol, excuse me, you can effectively get to compounds in the same way, but with a bit of control, again, because you can do this chemistry that would make a leaving group out of the nitrogen, right? And so that provides you with a little bit of versatility. Now, where pinnacle type rearrangements can often be challenging to students, and in fact where it shows up to a certain extent in the book, and the examples that the book gives of this process, involves reactions where you actually have cyclic systems. So we'll go through the example in the book, right? So in the case of the book, what it sort of shows is an example where if you have, say, for example, a ring, in the case of the book shows you have a 7-membered ring, right? And if you have I mean, you can do either size. It's just you're going to go from 7 to 8 membered ring in this case. Here's a good example, right? If you have a molecule that looks like this, right, or an analogous molecule like this with a pinnacle rearrangement, right, you're never going to generate cation character leaving group there, right? You're going to more likely generate the cation here, right? And so the example that the book gives is actually a really good one because I think it illustrates some of the benefits to this 1,2 amino alcohol reaction over, say, for example, the pinnacle rearrangement. Because if you do this chemistry, what's going to happen is now you'll selectively get a leaving group at that nitrogen. Okay? Okay, now, we don't generally like to make carbocation intermediates, and it may be the case that we're not generating carbocations in this process. It's very possible that this overall mechanism may in fact be concerted, right, such that all the bond formations are taking place at the same time, that you never generate a true carbocation. But again, because nitrogen is such a good leaving group, again, we don't generally want to see carbocation just sitting on a benzene group as well, right? And so from the standpoint of drawing a mechanism of a transformation like this, given that this is nitrogen leaving group, I'll give you a little bit of ability to go ahead and draw that carbocation intermediate because I do think that it's fair. But alternatively, what you can do is draw a concerted mechanism, where as the oxygen comes down to this avenue, let me do this in color just so you can sort of follow what I'm doing, the bond, that sort of bond that I've highlighted in blue, is going to shift over, making a bond between this carbon-carbon, and in the process kicking off that nitrogen. So it might certainly be a more concerted process. The net result of this, right, is that now instead of it being a 7-membered ring, we've expanded that to make an 8-membered ring. Okay? Right, and in this case now what we'll have is this molecule here, right, plus nitrogen gas. And then we'll simply just deprotonate that and get to the ketone. So the ability to perhaps perform sort of ring expansions, to go from smaller rings to larger rings through this process may be one advantage of this sort of reaction that's otherwise analogous to the pinnacle transformation. Again, it's got a fancy French name. But again, I usually just think of this as like an amino pinnacle. Okay? Any questions? Okay, so sort of revisit the reaction that we've shown here. With sort of primary amines. So again, this is what we would call a primary amine, right? If we take this compound and we just solve, the way that we gain entry into the nitrogen leaving groups is Na, NO2, right, as well as HCl, and what we'll get to is our diazonium salts. But if you sort of notice in this process, right, we've effectively gone from 2 protons here, and if you go through the process, you've effectively eliminated 2 equivalents of water throughout the process. And again, in order to do that elimination of water, what you're going to need to have, right, is a system where, say for example, you might need an intermediate like such as this, right, and what you can effectively do in this process is, have the alcohol plug off the adjacent protons, and effectively the overall system here is to liberate and sort of generate water and sort of drive the process. But you sort of need this proton here at some point, or I should say you need, if we sort of go to the intermediate, right, that's probably the more the better way to draw it, right? We need a set of lone pairs here that could effectively push out that water to get us there. But the overall process works with primary amines, but when you begin to move to secondary amines and tertiary amines, if you think about the mechanism, you're not actually going to be able to generate the same system. So if, say, for example, you had the same reaction, but instead you had a methyl group there, if we sort of think through the mechanism, what we'll see is that we cannot get that same diazonium salt. This is where sort of understanding the mechanism to an extent can be helpful. Right? And so again, if we sort of think about this being an active form, just for sake of pushing arrows, I'll just draw it in this form. It's a little bit easier to do, quicker. We can attack this molecule generate the quaternary ammonium compound that I show here, right? And at this point, it's going to be very difficult to liberate water, right? Because once we abstract this proton, and let's say, for example, we put it over on that oxygen, right? We might be able to get to a system that looks like this, but now what we have to start doing is generating new positive charges that we can't necessarily get rid of, right? So if I sort of continue this mechanism upwards, right? We're really sort of stuck here. We can't really go anywhere. And in fact, this versus the deprotonated form of this, it's eventually going to go to the sort of sink. And the sink ends up being this molecule here. So when you have, I think that, these molecules aren't really going to be that useful for us for synthesis. But what's important to recognize, I think that's more important, is that you can't generate the sort of diazonium salt. This is the bigger take-home lesson here, because I don't see this being synthetically useful for you guys. But it's just important to recognize that a secondary amine isn't going to be able to lead to that diazonium salt. So you have to recognize that a primary amine is necessary to generate diazonium, and this sort of reaction is actually what would take place in a secondary amine. If you move to tertiary amine, again, you can look in your book. I'm not going to go through this, but as you might imagine, tertiary amines, it's the same issue. In fact, it won't react at all. So I think that's the most important thing to take home about this overall process in diazonium formation with different amines. It's that primary amine is important. If you think about it, the overall process, you need to effectively liberate 2 equivalents of water, and 2 of the protons that come from that water effectively come from the 2 protons on that nitrogen. So it's important that you have a primary amine here. Okay, so that's all really I wanted to say about that. All right. All right, so we've got one last reaction to talk about for amines, and it's a kind of neat one that I think is perhaps one of the more interesting reactions that we're going to learn, and it's perhaps one of the most unique reactions that we'll learn. And there's some important stereochemistry involved in it as well, so I'll spend probably the next 10 minutes discussing this reaction, and then in the last sort of half hour to 40 minutes or so, we'll sort of review what we've learned so far. I can sort of open up the floor to questions and so forth. So we sort of learned in the case of, we just take a step back for a second, we learned that if you have a system where you have let's just say Me3, right? Right, we have sort of a quaternary ammonium salt. We've seen sort of chemistry where you can sort of generate this from the tertiary amine, simply treat this with a base. Right, and what can happen is the Hoffman elimination process. And so this is one way that you can take an amine and sort of generate an alkene. This is one type of elimination that we've seen in the past. That simply you take the nitrogen, turn it into a leaving group, and then do just elimination chemistry. And the interesting thing about this one, again, is that the less substituted alkene will form. And again, it has to do with the sterics of the leaving group. But there's another actually really interesting elimination reaction that I think is worth sort of bringing up, and it's called a coelimination. Okay, and in a coelimination, what you'll do is you can take a molecule, similar molecule. So let's say we have dimethylamine. So we'll just sort of draw the parallel here. And instead of taking this and treating it with bromomethane and making the quaternary ammonium salt, what you can actually do is you can take this molecule and you can oxidize it. And it turns out there's lots of conditions that you can do to oxidize amines. The one that the book uses is hydrogen peroxide, which is a good oxidant. And what happens in this case is hydrogen peroxide, or you can imagine this working with things like MCPBA, for example, as well. It's effectively an electrophilic source of oxygen. Okay, so what will happen is, again, you can imagine a mechanism probably a little bit more complicated than this because OH isn't necessarily something we think of as being a good leaving group, but you can have this molecule that's referred to as an N-oxide. Okay. Now, what's interesting about this N-oxide is that in some ways it's analogous to the quaternary ammonium salt that we generated in the Hoffman elimination, right? In that you have this positive charge on the nitrogen that might be satisfied if we can get rid of it. But what's interesting in the Cope rearrangement is that, in fact, we end up having an internal base. Okay, so unlike in a situation like the Hoffman elimination where our hydroxide came and plucked that off, in this case what we have is actually an oxygen base that's actually right in there. Okay, and so what can happen here is we can actually do effectively an internal deprotonation. And as we'll discuss, this is what's called a syn elimination. Okay, so it's analogous to this process here, right? The hydroxide's attacking the proton. We're breaking that bond, making a double bond, and pushing these electrons onto the positive charge of this nitrogen. It's the exact same thing that's happening here, except that it's an internal process, right? The net result in this reaction, again, is that you're going to get that that alkene, but the overall reaction, again, is going to sort of liberate this hydroxylamine. That's sort of secondary importance. It's not really that important. But the more important thing is that this ends up being a concerted process, and this is what we would call a syn elimination. Okay, and so let's sort of review very briefly stereochemistry in an elimination reaction, our standard E2 elimination reaction. And let's discuss how a syn elimination is different than our standard anti-elimination. So if we can remember, our standard E2 reaction, you can in fact do an elimination with sort of a stereochemical outcome that's actually predictive based upon the mechanism of an E2. Right? And so if we think about our let's just discuss any. So if we have an alkyl bromide and we start putting some substitution onto this molecule, so let's put a proton there, let's put an ethyl group here, let's put a methyl group here, and maybe we put a methyl group here, right? When this overall elimination takes place, right, we're going to generate, you should be able to see fairly easily that we're going to generate one of two compounds, right? So we're going to generate an alkene, we've still got our proton over here, and we're going to get one of two compounds. These will be either this compound here, right, or sort of reverse this compound here. So effectively, either the methyls can be on the same side or the methyls can be on opposite sides from one another. And in fact, if this was an E1 reaction, you might get a mixture of both. But one of the things that, if you think back to organic 2, is that only one of these two is going to form. And we can, in fact, predict that, right? Because what we know is that in an elimination reaction, what is required, right, is that we have the alignment of our electrons within that hydrogen bond align with the sigma star of the carbon-bromine bond. So what's necessitated is what we call sort of anti-periplanar. So we need, again, the bromine and the hydrogen in the same plane of the board. And again, as we start to look at this molecule, we can't really necessarily, as it's drawn right now, judge that because it's not in the right configuration. So it makes it very difficult sometimes to actually figure out, just looking at the molecule, which diastereomer would form. And so oftentimes what we would have to do, and you'd probably be really good at this if you practiced actually rotating bonds to figure out what RNS is rather than learning rules, you could rotate around this bond, push the proton up, push the methyl group back, and you would see that rotating around this bond, right, as you push the proton up, right, and again, I maybe should have just had the proton go down, so I made it a little bit more difficult, but again, we can go through this. So the proton's going to go up, the methyl group's going to go back, the ethyl group's going to come here. In the case of the bromine, I'm going to have to rotate a full 180, so when I do that, the proton's going to be coming towards me, and the methyl group's going to be going away from me, right? And when this elimination takes place, the ethyl and the proton are on the same side of the molecule, right? The methyl and the other methyl group are going to be on the same side of the molecule. And so what we see is that the actual product of this reaction is this one here and not that one there, right? Does everybody see that? Now, the difference in this process is that this is what we would call an anti-elimination. Again, we have the proton and bromine anti to one another. In a cope elimination, or any syn elimination, so cope is simply one example of a syn elimination, as we'll see, we can actually get the opposite. Because what needs to happen in a cope rearrangement, right, is if you are doing the analogous elimination, if I just draw the exact same molecule, but I'm just going to make my leaving group now the N-oxide. Right? Now that sort of internal base is on the whole other side of the molecule. So in order for a syn elimination to take place, again, it should be straightforward. Instead of it being anti, we need to make the process syn. Right? And so if we rotate around this bond, what we will see is that you have the ethyl group here, and you have the methyl group there. As we rotate that bond around, now the methyl group is coming towards you, and the proton is going away from you, right? And so you've effectively inverted the relative stereochemistry in the elimination process. Thus, when you actually do this reaction, now the product that you get is going to be the opposite one. Again, the ethyl and methyl are on the same side. And the proton and the methyl group are going to be on the same side. So again, the important point here is this is a different type of elimination. It's different than what you guys have seen in the past. But as you can sort of see, there ends up being this sort of stereochemical outcome that could arise from this reaction. Okay. Now, one of the things about cope rearrangements in general is that there's an element within this that has to do with if you have multiple groups that could be protonated, right? And so in sort of these cases, I'll just sort of explain it to you. So this is great for generating this certain stereochemistry, but there are some limitations to the cope rearrangement. And part of it has to do with the fact that since you have an internal base, a lot of parameters such as sterics can't necessarily be overcome. And there doesn't seem to be a preferential favor for other compounds. So if I just sort of, I'm not going to worry about stereochemistry right now, I'm just going to sort of draw a different molecule. Right? But if you have a molecule like this, and you want to do a cope elimination, you actually have two protons that can be eliminated, right? So you have proton here, and if you eliminate from the green proton, again, the product that you'll end up getting will be that one there, okay? In the case of the other proton, which we can show in blue, right, we'll get the internal alkyne, or sorry, the alkene. Okay, and in this case, it turns out that there's not as dramatic of a stereoselectivity. I would think for your guys' sake, you know, if you were to predict one, which one might you guys predict? If there's not a steric component, there'll probably be an electronic component. So, yeah, you probably want to assume that it's going to go to the more sterically accessible. So, you know, again, it is non-selective, so in a synthesis problem, you know, in a real synthesis where you're actually performing it, you might not want to do it. In your guys' case, that gives you a little bit of flexibility to say, well, I would make some of this one, right? Generally, where the selectivity can come into place, and this is what sort of offsets this a little bit in terms of, it's usually what proton is more acidic. And so if there happens to be a proton that might be a little bit more acidic than the others, you can actually get some more selective regiochemistry. And what I mean by that is, let's say, for example, I have an alkene at that position, right? You can think about the anion being generated there as being stabilized through that alkene. And so in a situation like that, you might more likely generate the internal alkyne because that proton's more acidic, right? Meanwhile, say, for example, if you were going the other way, if, say, for example, you had a phenyl group there or something, right? Now that proton here, right now this proton here is effectively stabilized by the phenyl group there. So in general, the better selectivity often comes through instances where one of the protons might be more acidic than the other, generally through some type of stabilizing interaction. So, and I don't even think alkenes work that way. Aryl groups work pretty well. But you can imagine the same type of idea with alkenes, just not as pronounced. So it's a little bit more difficult to get regiochemical control in a cope, but there is that advantage of the syn elimination. So in general, people like to use cope eliminations when there's only one possible outcome. Okay? Okay. All right, so that's the important take-home lesson with the cope. You should be able to, if I give you a cope reaction, you know, you should be able to give me a second. You should be able to provide the stereochemical outcome of that alkene, right? So you should understand that and be able to explain the syn elimination. So I'd expect you guys to be able to do that. Yeah.
Why would it be the top one on top of it? Isn't it still like a bulky?
Right, but where's the base? It's an internal base. So it's right there. It's already there. In the Hoffman, you actually need the base to try to come in. Right? So it actually has a steric component where you're actually trying to get the base to come in. In this case, it's already there.
But also in the video that I watched, it was kind of like a carbon anion character.
Mm-hmm.
So wouldn't it be better to make it on the top where it's less from?
Well, that's what I was just saying, right? So it's the one that's the more acidic. And that's, you're effectively saying the same thing. Carbanion character is ability to stabilize the negative charge. Right? That's why I'm saying, in general, like a situation like I drew, yeah, your thinking is kind of right there, that a primary proton is more, so I like the way you're thinking. The primary hydrogen is less substituted, thereby it is more acidic. But that's a very subtle difference in acidities between, I think the pKa difference is like, one is 50 and the other is 53 or something like that. So it's very, they're relatively similar. If you now put some type of stabilizing group, that will drop the pKa value effectively of that enough where you can begin to start seeing more pronounced differences. So you're right, yeah, anion, the one that generates better anion stabilization is the one that forms. And so from that standpoint, it would be perfectly valid to predict this is the major product. Certainly because it's a bigger, right, so certainly because it's an internal base. Well, no. I'm not saying, in this case, without the alkene there, you would get a mixture.
Oh.
Yeah. Without the alkene there, you get a mixture. I just was showing that once you put some stabilizing group, I was basically trying to say exactly what you just said.
I'm talking about the alkene.
It would be non-selective. Yeah, it would be non-selective. It might be a slight major product. And you could argue that it could be through, according to what you read, it's kind of that, what I was just explaining in terms of acidity. So you might argue and predict, right, that this primary proton would be more acidic based upon the fact that it's primary. And so you may end up predicting that there would be some slight preference for this one. But you could also, at the same extent, make a thermodynamic argument that would go to the other one. And so it ends up being very non-selective unless you have some stabilizing to actually drop the pKa of that proton substantially. Yes? So that's the trend that we generally see, right? So if you think about, it's just one of these patterns that we've seen. So for example, with carbocations, right? For carbocations, tertiary is more stable than secondary, and it's the opposite for anions. And so that's what Daphne's saying, is that the primary anion, which effectively would result from the negative charge generating there, would be more stable than the tertiary, which is there, until you then put in the additional stabilizing factors. Right, so as soon as you take something like this and put, say, for example, a benzene group there, now this might be more stable than that because of resonance stabilization. So now, again, I don't know the exact numbers, but something like this might be more stable because of resonance. And that's what I'm saying, is that there's this sort of electronic preference stabilizing it. So secondary versus primary versus, so for anions specifically, again, we're not generating a full-fledged anion, right? This is a concerted process, and there's a buildup of anionic character. And it turns out that that's not, the difference between that on a primary versus a tertiary really is not all that different. Oh, sorry. Sorry, yes. Sorry, yeah. Okay, yes. Yes. Well, it's not yeah, I mean, there's always anytime we get to things like concerted and non-concerted processes, you're sort of saying that it's fully concerted. And it is a concerted process, but whether the electrons are shared globally throughout that system or not is not necessarily accurate. Think about the regiochemistry in a Diels-Alder, for example. Right? So even though the Diels-Alder is concerted, there are buildups of delta minus that can sort of dictate that. So that would be a good analogy as the Diels-Alder, which is aconcerted, but there are still impacts that can be generated based upon electronic arguments. Up here, this one versus this one. Without the alkene there, they're basically going to be virtually the same. Perhaps a slight preference for this, but basically the same. Until you start adding stabilizing groups to stabilize that anion. Okay, any other questions on coelimination? So again, what I'd really like you guys to be able to do is draw stereochemistry of copes. Like, what is the coelimination? Can you draw in a stereochemistry? That's something that you can expect either on a quiz or an exam. All right, so for the last half hour, what we'll do is I'll open up the floor to more general questions for starters. And then if we have time, we can, I have a few sort of synthesis problems within aromatic chemistry that we can perhaps go over. I should point out that I in general am not a big fan of the questions that are in the book. Well, I think they're okay questions, but I generally will point you in the direction of my questions. I did find that as I was looking through the aromatic chemistry chapter, I don't think I was actually that good at coming up with questions for the aromatic chemistry as I felt with the other, in part because I'm not as familiar with that chemistry, and so it didn't come as natural to me. When I actually looked through the book's questions on that, I actually really liked a lot of the questions that the book had for the aromatic chemistry chapter. So I would urge you guys to really, maybe even more so than my worksheet on the aromatic chemistry, look at the book questions, because I think they have really good ones, specifically for like synthesis questions and how to address questions of regiochemistry within aromatic chemistry. So I would definitely use the book's questions for aromatic. I would always use the book's questions. But I usually will first point you to my questions, but I do think that the book with the aromatic chemistry has some really good stuff. So, all right, so questions. Anything that you guys would like me to do in particular? Okay, so I've just scribbled down a couple synthesis problems just to sort of get us thinking about, yeah. Which one? That's what I just did. That's the dipnu. That's the 1,2. That's the amino alcohol. Oh, you want me to go over it again? If we're to have a problem that's perhaps a little bit more complicated, right? Maybe I'll take it in this direction. So the question was, can we go over pinnacle style chemistry within the context of something a little bit maybe more difficult to see? There are questions that we might be able to do where the products might be perhaps a little bit more difficult to see right off the bat, and I think particularly with alkyl shifts and so forth, sometimes figuring out what the product is, there can be a lot of mistakes in terms of knowing what all the carbons in and so forth. So to go over a problem like this, this would be an interesting question to say, here's here's the, whatever they call it, whatever it's called. Let's just call it a Zito pinnacle, right? And we want to treat this with NaNO2. And the question would be, predict what the product is. So why don't you guys try to sketch this down and think about what the product would arise from this reaction. There could be a couple possible outcomes. And in fact, I would say there's two possible products that would form. One of them might be a little bit easier to see than the other, but I'd say let's sort of discuss the compounds that can form. There's two products. Let's look at them and let's ask ourselves, one of these look like it would be more likely to form than the other. And again, if you remember, the first step is simply going to be to generate N2, right? We're then going to generate the carbocation, and then so the question really becomes, is at that step, where is our alkyl migration going to take place, and what is the resulting product of this? And again, there's going to be two possible products that I want you to consider. There's the migration of this bond, and there's migration of this bond. And so let's look at both those possible migrations, think about what the resulting products will form from them. And we can start with the green one. We'll start with the green one first.
What would you want to use?
Okay, and so there's two possible alkyl systems in place. We'll practice drawing the products, seeing what would result from them, and perhaps if we're struggling to see this or draw this, perhaps we can discuss ways that might make it easier for us to see. Oftentimes redrawing in different ways can be helpful. So I would hope in the case of the green bond moving, this should be fairly straightforward for you guys. Right? So again, if this is the case, if we're going to draw this shift, right, what's going to happen is that bond, right, is going to go up. Sometimes you can just draw a dotted line to show where the bond is going to form. Right? So effectively what we're going to be doing is this green bond is now going to be up there. And sometimes when you're drawing these molecules, again, I allow pencils on exams, right? So sometimes what it's worth it to do is just redraw the molecule, right? Say, well, I'm deleting this bond, so let me just erase that bond. Right? And what's going to happen is that's going to come over here. And the result is that I'm going to have a positive charge right there. Everybody see that? So I sort of redrew the molecule. Again, this is one of the advantages of doing something in pencil. You can just simply redraw the molecule. Second time, redraw it. After you've sort of shown what your arrows are going to do, and then what you can do is simply take the bond that you want to move and perhaps move it up there. The result in this case is going to be that you're going to push the electrons down. And what you will have in this case is a 5-membered ring, right? And then we're going to have 1, 2, 3, 4 carbons. So if we just start numbering these, because that's always sometimes helpful. All right, so there's 9 carbons total. Maybe I can go back and look at the first one just to make sure. 1, 2, 3, 4, 5, 6, 7, 8, 9. And again, as you see in the green line here, what we've done is we've made a bond that was initially going from the 9-4, and now it's going to the 9-3. Okay? So we've got 3, 4, 5, 6, 7, 8. And again, and we can sort of map and see, yep, our 7, 8 is together, or 7, 6, 5, and you can go all the way around. And again, at this step, then you would simply deprotonate that, and the net result would be molecule here. 1, 2, 3, 4, 1, 2, 3, 4. Okay, so does everybody see how that one works? Okay. Now the bottom one is going to be the one that's perhaps a little bit more difficult to draw, right? Because, and really the whole reason why it's more difficult to draw is really because of the way that I actually have it drawn here, right? What makes doing an alkyl shift, it's going to be the exact same mechanism. It's going to be the exact same overall process. But what ends up making it difficult is the fact that this is sort of bunched up in this sort of region here, right? It's maybe a little bit difficult in part because of where everything is bunched up. So one thing that you could imagine doing, right, we could still try it through the same process, but sometimes it's worth it to redraw. But let's just try it without redrawing it for starters, because maybe it's not as difficult as we would think. Okay, so if I do the same thing here, what I'm going to do is just something slightly different, and that's just that I'm going to come out a little bit. Because I think part of the problem here, all I've done is I've tried to move these to the middle a little bit more as I'm redrawing it. And the reason I'm moving them a little bit more is so that we can sort of, the bond from there to there might overlap a lot. I know that I want to make a bond from here to there eventually. So what I'm doing here is I'm just bringing it out such that you can see that a little bit better. It's the exact same molecule. It's got 3 carbons on top. It's got the 3 carbons on the bottom. 1, 2, 3, and it's got the 1 carbon in the middle, right? And so what we have here is a positive charge there. And the other thing that I'm going to do when I redraw this is I don't want that alcohol in the way of what I'm seeing. So I'm just going to move the alcohol inside here. I gave myself a little bit of space. So I'm just going to move that alcohol. I'm just going to redraw it with the alcohol coming in. It really hasn't changed anything, but what it's doing for me is it's allowing you to take that blue bond here and more accurately see the new bond that's forming. Everybody see how I did that? So I didn't change it that much. I just effectively puckered these in a little bit and moved the hydroxyl out of the way. And what that's going to allow me to do is begin to sort of map the bond forming between here and there. Okay? So again, if we sort of think about that bond that we're forming here, it's going to be that bond right there. At this point, poly, right, what we might want to do is number, right? We might want to number our carbons in the same way. Right? And that's going to tell us right away that the new bond that we're making, right, is between what? It's between the 5 and the 3. And we're breaking the bond between the 4 and the 5. It's just going to help us map the system. Again, as I said earlier, sometimes you can just simply redraw the molecule over here. Just not make any changes yet. But just notice that I'm going to make this bond here, and it's going to be this one that I'm going to break. So in this case, what I'll do is I've sort of redrawn the molecule, but what I'm going to do is now I'm going to make a bond between here and there. And the result is that I'm going to have a positive carbon on that bond, right? So I just redrew the molecule, and then I erased the bond that was breaking. There's the bond that's forming. So what I can do is and what I would do to make sure that I'm not missing any carbons is count them all. And I would go 1, 2, 3, right? And what I would notice is what you guys noticed, right? Which was that I was missing a carbon there, which is right there. And that's, again, I've been doing this for 10 years, and I would have caught myself once I counted. And so that's just important to recognize. Right? 6, 5. Right? So when we go through counting it, so again, what did we say before? We're going to break the bond between 4 and 5. So we no longer have that bond between 4 and 5. We now have a bond between 5 and 3. The bond is now between 5 and 3. Now what we have here is a 1, 2, 3, 4, 5, 6 membered ring. And again, we can number it for 4, 9, 8. Again, because the 1 is bound to the 8, right? And then we have 8 to 7. So basically what we're doing here now is we're going to have electrons going from 3 to 8. So we have 3 to 5, 5 to 6, 6 to 7, 7 to 8. Right? So 3 to 5, 6, 7, 8. Right? And what's missing? Now we've got our carbon backbone. What's missing? We have to put in the oxygen and the positive charge. That's on carbon 4. I'll bring carbon 4 in there. right? So that's the 4 is what's bearing the positive charge. Again, so we're pulling electrons away from it back here, so it should all make sense. And again, when we're all said and done, we'll have something like okay? Right, and so as I look at these two products, I might want to be able to predict which one is more stable than the other, but actually now that we've drawn them, anybody got any feeling for which one might be more stable than the other? Yeah. Yeah, I don't really think that we could at this point. I think that we would need to perhaps, nothing screams out horrible for either one of them. Perhaps if we made a model, that would be the case. So I might guess that this would be a process where we might get a mixture of sort of isomers. But again, there may be some subtle difference in energetics of the two. So again, this is what might be difficult with the pinnacle type reactions, and that's going to be standard, I think, for any alkyl shift. I think sometimes when you begin to rearrange carbon skeletons, especially in ring systems, it can sometimes be difficult to see what those are. So I think that's the take-home lesson for this type of mechanism. That's where, if you know the mechanism, then simply the next step is can I draw it if it's packaged a little bit differently? Okay? All right. All right, make sense? All right. All right, so let's do a synthesis problem. Okay, so let's pretend that the year is 19. So it's a different world that we live in, and I isolated two compounds in a reaction, and the two compounds that let's say I was doing natural product chemistry. I extracted a bunch of organic compounds from a tree, and two compounds I identified. One was active and one was not active, but I couldn't figure out what my isomeric mixture was for some reason. And the two possible regioisomers that I had were this one and perhaps this one here. So sort of meta substitution and para substitution, and for whatever reason the NMR technology wasn't around, so I couldn't just simply look at a molecule and look at NMR signals. But what we did know at the time was relative regiochemistry of aromatic chemistry. Okay. If we wanted to synthesize these molecules, if I wanted to synthesize this regioisomer and this regioisomer, we should be able to, using the chemistry that we know now, be able to propose syntheses for each of these molecules. Okay? And part of this is simply going to be, well, part of it is going to be remembering the reactions, right? That's kind of the essential component to any synthesis problem, which obviously takes time. But the other issue is, once you know those reactions, another aspect to it is going to be, what's the order of these reactions? Okay? So let's think about how we would make this, and I'd like perhaps some of you guys to take me through the answer. So everybody spend a minute or two. We'll just sort of sketch out a few answers, think about what we're going to do, and then think about the order that we want to do it in. I would say a question like this would be a very good quiz question. Okay, so I always like putting synthesis problems on quizzes for aromatic chemistry. This is the sort of type of question that I think is good for quizzes. And again, in any synthesis problem, there's often multiple ways to the same answer. In this case, you should be able to do this in 2 steps apiece, but there might be 3-step processes, 4-step processes that might also lead to the answer. But Got it?
It's crazy. Like, let's say how do we think about this?
No, it's 2 steps. Probably make it 2 steps. Yeah. Okay, hold on. So I'll just give it a minute and then I'll let you answer. Let's let everybody think for a little bit. All right, so for the first question, just by a show of hands, how many people think they got it? How many people have no idea? Okay, well, it's good that not many people raised their hand the second time. I don't know if that's just because they were embarrassed to raise their hand or not. So let's discuss it. So what's your name? What is it? Nada? Nada. So what do you have for an answer? Yeah, for the first one. So what would be your first step? So if we're starting from benzene, what's the first reaction you want to run on it? So we need specific chemistry, specific reactions that are going to specific groups, not more general reactions. Okay, so what's that going to get us to? Nitro group. Okay. So you want to put the meta group here. So the ketone. Okay, so what we're going to do now is, how do we make the ketone? How do we put the ketone on there? Okay. Okay, so now we've got the substitution. Now what we got to do is convert that nitro into the methyl group. So how are we going to do that? What's that? How do we remove a nitro group? Who wants to help him out with the nitro? Let's not take a step back. Let's keep moving forward with this. Nitro, yeah.
I just make the you need to say the agent
Right?
to make an answer, but I'll just put it.
So what you want to do? So I think if what you're saying is you want to go to the N2 leaving group.
Right, isn't that what he's trying to do?
I suspect that's.
I thought that's what he was doing.
Right, so that's the question, is how do we do it? So the first step would be a reduction of the nitro to the amine. How do we reduce a nitro? Yeah, so let's just, yeah, there's a few different ways. So let's just say nickel H2, right? That's going to get us to the amine. Then we're going to generate NaNO2, HCl. That's going to get us to N, right? Now we got to convert that to a methyl group. So how are we going to do that? Daphne. That's a great point that Daphne just brought up. Maybe the H2 and nickel. Certainly LAH would. Use rhodium. There's almost certainly, yeah. So there's almost certainly a catalyst that could reduce. Well, yeah. Would rhodium and hydrogen? Yeah. Yeah, I mean, this brings up a big question. I don't think this is the best way. We're just trying to move forward. So let's say there's a big question mark here because of reduction. Perhaps rhodium and hydrogen might be selective. I'm sure there is a method out there to reduce a nitro in the presence of a ketone, but again, that might be a problem with the synthesis. Yeah. Yeah. No, yeah. But let's move forward with this one. Yeah, I mean, so at this point, what we need to do is we need to put a methyl group there, and so iodomethane is not, that's an electrophile. What you need here is nucleophilic aromatic substitution, and I think that we could get here. I think that what we would want to do, but we'll learn this chemistry, I think, next week. What we would probably do if we wanted to go through this approach is that we would want to effectively displace that with a halogen, right? So let's say HBr, copper bromide. And then we'll see next week that you can take, there's palladium catalysis where we could take this and use like trimethyl tin and palladium, and we could put that methyl group there. But we can clearly see that that nitro group, I understand the thought process. It was I want a meta director. But the bottom line is, you may already have a meta director in here. Okay, so I like the thought process, but let's start over. All right, so what is our meta director here? Yeah. Yeah, the ketone. This is a meta director. So you don't need the nitro, because the nitro just gives you more problems. Yes, it's going to direct, but then you create a new problem, which we might not be able to do. So it's important to recognize in this problem that this is a meta director, this is an orthopara director. So what we'll do is, the first step will be, Friedrich Class isolation. So we'll use this and aluminum trichloride or something. Okay, and then once we have this on there, now how do we put a methyl group in? Here's the Friedel-Crafts acylation, Friedel-Crafts alkylation, right? So what we would do is basically the same thing. You would do MABR and let's say AlCl3. Right, and what we'll get is this position here. Yeah, it's possible we might get over-alkylation, but this, in aromatic chemistry, we'll try to give this the 1, okay? So what would happen if we did it the other way around? Right, so now that's the whole point of what the problem was, right? If we start with benzene and we reverse these, right? We'll get the methyl group. And then if we now take this, we'll get ortho-para. So we'll get some of the para, we'll also get some of the ortho. So, all right, so with that, just this whole point of this question was recognize that if you're doing substitution, sometimes the order of the reactions will dictate this regiochemistry. Okay? All right.